Welcome, my friends. In this video, I'll be discussing section 5.2, confidence interval for the population proportion. Remember that if we have categorical data, then we will typically calculate a proportion. For example, a February 7th, 2022 poll found that 685 out of 2005 registered voters could locate Ukraine on a map. The possible outcomes for this variable are either yes, someone can locate Ukraine on a map, or no, they cannot, which is a categorical variable. The most common way to summarize categorical data is to calculate the proportion of quote-unquote successes to the total sample size. If we wanted to calculate the proportion of voters sampled who can locate Ukraine on a map, we would take the 685 individuals who could locate Ukraine on a map and divide by the sample size of 2005. The result would be approximately 0.3416, or 34.16%. We would use p hat to represent this value because this is a proportion that is based on a sample. In this section, we discuss the confidence interval to estimate the population proportion p. In our example, we only had a sample of some registered voters, so we only had the sample proportion and not the population proportion. If we want to estimate the population proportion, we either have to have a census of all registered voters, or we can take a sample and construct a confidence interval to which we can be, for example, 95% sure the true proportion falls within. Here's the formula we'll be using for the confidence interval for the proportion. P hat is, of course, the sample proportion, which we find by taking x, the number of successes, and dividing by n, the sample size. In our example, the number of successes was represented by the number of individuals who could locate Ukraine on a map. The z-value is the z-score, which we will find using a calculator function called inverse norm, which could also be found using probability tables. Q hat is the proportion of failures, which is the complement of p hat, or 1 minus p hat. If p hat is the proportion of individuals who can locate Ukraine on a map, then Q hat would be the proportion who cannot. We call the sample proportion p hat the point estimate of p. It's our best estimate for the value of the population proportion. For example, in our case, our sample proportion was 0.3416. We estimate that 34.16% of individuals in America who are voters are able to locate Ukraine on a map. But of course, this does not represent all Americans, so we say this is an estimate for the value for all Americans. Everything after the plus or minus is what we call the margin of error, sometimes just called the error. The margin of error is made up of two different parts. First, we have the z-score, which is sometimes called the confidence level multiplier, and then we have the square root of p hat q hat over n, which is called the standard error. The standard error is a measurement that represents, on average, how far the sample proportion will differ from the population proportion. The best way to visualize all this is to look at a number line. Our point estimate, or p hat in this case, will go at the center of our confidence interval. We'll have the lower bound somewhere a little bit less than our p hat, and the upper bound a little bit above p hat. The distance between each of those is what we call our error, which is made up of z times the square root of p hat q hat over n. Now, anytime that we do inferential statistics in this class, meaning when we're drawing a conclusion about a population based on a sample, which a confidence interval is one example of, we're always going to be using something called the Fred technique. The Fred technique was created by Grand Valley textbook author John Gabrosik, which is named after his dog, Fred. Each letter in Fred is going to represent a step that we'll be taking whenever we do this process. F in Fred stands for formulate the problem, R stands for review conditions, E stands for execute calculations, and D stands for draw conclusions. And here's a picture of Fred, just in case you were curious. He shows up quite a bit throughout the Grand Valley textbook. So how do you apply the 4 steps of the Fred technique to a confidence interval of the population proportion? Well, I'm glad you asked. For formulating the problem, there are many things that you must do. First, you must describe the population. Secondly, you must describe the sample. Third, you must describe the categorical variable which you have collected. And finally, you must describe the population parameter using proper notation. Don't worry, we'll have examples of doing all these steps later in the video. Next, we must review the conditions. Every single confidence interval that we do, and in fact, every inferential statistical method that we do, will come with its own unique set of conditions that must be met. If these conditions haven't been met, then we really shouldn't be doing this procedure. Now, it's not explicitly stated in the textbook that this is a condition that we must check, but it turns out that for basically every inferential statistical method that you do, for either a confidence interval or hypothesis test, we typically always need a random sample, meaning that every individual in the entire population should have an equal chance to be chosen at any stage of the sampling process. So don't forget that that must be met as well. But the only condition we're going to be checking for the confidence interval on the proportion is that n times p hat and n times q hat are both at least 10. This relates to something called the central limit theorem, and since we're utilizing the z distribution in the formula, we have to have both of these values at least 10 in order to move forward with the confidence interval. And these two things can easily be calculated from a sample, so this is no big deal. Next, we have the execute calculation step, which is typically the longest step. This is where we will be completing the formula that we looked at earlier. Finally, we can draw conclusions, which just amounts to filling in this template statement. We are C% confident, where C is your confidence level, that the interval between the lower and upper bound, which are the two numbers you got from the formula in the execute calculation step, contains the, and then you'll describe the population proportion, which is something that you already did in step 1. Okay, there's one more thing we need to discuss before we can do a full example, and that's how to find the z-score in the confidence interval formula. Here is the confidence interval formula. To find the z-score, we're going to be using a function in the TI-84 called inverse norm. This function takes in 3 different inputs. First, the area to the left, and then 0 and 1. We will always put in 0 and 1 for the last 2 arguments because 0 is the mean of the z distribution and 1 is the standard deviation. To find this function, we will go to second vars inverse norm on the TI-84 calculator. So really the only thing that we need to determine is the area to the left. This is based on our confidence level. So let's say we have a 95% confidence interval and we would like to find the z-score. Then what you should do is draw a picture of a standard normal distribution, or z distribution, and put your confidence level in the middle, which is 95%. From there, you need to determine the area in each of the 2 tails of the distribution. Well, if the entire distribution adds up to 100%, that means we must have 5% left over to get to 100. 5% divided by 2 is 2.5, so we must have 2.5% in each of the 2 tails. Note that the z-score that we're trying to find is always the z-score on the upper bound of the shaded region. So right at the boundary of the right-hand tail here is the z-score that we're trying to find. Now we need the area to the left of that z-score. Well, the area to the left of that z-score is really 2 different areas. It's the area in the middle of 95% plus the area in the left-hand tail of 2.5%. 95% plus 2.5% is equal to 97.5%. So we need to use inverse norm with 97.5%. Let's head to the TI-84 calculator. On the calculator, we can press the second key, and then the vars, or distribution key. And let's make this a little bit smaller here. And then we're going to want to scroll down to the third option, which is inverse norm. When it asks for area, it's asking for the area to the left, which we just said is going to be 97.5. Now we need to put this in decimal form, so it's going to be 0.975. You should always leave the last 2 arguments as 0 and 1. Go ahead and paste, and this is the way that it might look on an older TI-84 or maybe a TI-83 calculator. You'll have to enter these 3 arguments separated by commas, and that comma is, of course, right above the 7. When we press enter, we will get 1.96. Now I should mention that some calculators do give you the option to change the tail area. So you may have the option to change it to area to the right or area in the center. But my advice is to always choose the area to the left to match the way that I'm doing it in the videos and in my PowerPoints. And also there will be some other functions we use later that won't have the option to change. So it's a good idea to get in the habit of always using the area to the left. But that doesn't affect everyone. That only affects people with the rechargeable versions of the TI-84. Let me just show you so you can see what I'm referring to. On this version of the TI-84, when you do inverse norm, you have this option for tail. And my advice is to always leave this as left to match the way I'm doing it in the videos. Anyways, the z-score that we get is 1.96, which is the value that we would use in the formula. Okay, so here's a chance for you to try this. So see if you can find the z-score for each of these three circumstances. So what you're going to want to do is draw a distribution, put whatever percent confidence interval you're dealing with in the middle, find the two tail areas, add up the middle area and the area in the left tail, and input that into inverse norm in order to get three different possible z-scores. So go ahead and pause the video and give that a shot. Now, I'm not going to give you the answers here, but just notice that if you did this correctly, the z-score is going to get larger as the level of confidence increases. So the higher your percentage here, the higher the z-score, which should make sense, right? If we go back to this slide, if you have a higher percent in the middle, that's going to push the z-score a little bit further to the right. And that actually is why when you increase the level of confidence, it increases the margin of error in a confidence interval. Remember, the margin of error is z times the square root of p hat q hat over n. And you may remember from a previous video that we said when we increase the level of confidence, we increase the margin of error. Now we're seeing that in the formula. When we increase the level of confidence, we increase the z-score, which is part of the margin of error formula. Okay, at this point, we are ready to look at a full example. So this is the example that we used in the intro to this video. A February 7th, 2022 poll found that 685 out of the 2005 registered voters that were sampled were able to locate Ukraine on a map. We want to find a 95% confidence interval for the proportion of registered voters who can locate Ukraine on a map. So we're going to be following the 4 steps of the Phred technique. So the first step is to formulate the problem. We then formulate the problem. The first thing we need to do was to describe the population. Whenever you describe a population, you should use the word all. So in this case, the population is all registered voters in the United States. Next, we need to describe the sample. The sample includes the 2005 registered voters that we sampled. Next, we need to describe the variable. Remember that the variable is what we collect from each individual. Each individual, we're collecting whether or not they can locate Ukraine on a map, either yes or no. This is a categorical variable because the options are non-numerical. It's either yes or no. Finally, we need to describe the parameter that we're trying to estimate. We are trying to estimate the proportion of all registered voters who can locate Ukraine on a map, or in other words, the value of the population proportion P. Okay, next we can go ahead and move on to the second step of the Phred technique, which is review conditions. The only condition that we need to check is that n times p hat and n times q hat are both equal to at least 10. So what we should probably first do is write out some of the given information and the symbols that correspond to them. So we had 685 individuals who could locate Ukraine on a map, and we use x to represent that value. Our sample size of 2005 is n. We may also want to write down that we have a 95% confidence level, so we could say CL is equal to 95%. Next, we can calculate p hat, which is the proportion of successes, or proportion of individuals who can locate Ukraine on a map. And we can do that by taking x over n, or 685 divided by 2005, which is equal to about 0.3416. About 34.16% of the individuals from our sample could locate Ukraine on a map. Next, we have to calculate q hat for the formula here. So q hat is equal to the complement of p hat, or 1 minus p hat. So 1 minus 0.3416 is equal to 0.6584. 65.84% of the individuals in the sample could not locate Ukraine on a map. Next, we need to plug into both of these formulas. So n times p hat is 2005 times 0.3416, which is equal to 685. And it turns out that that value is actually the number of successes, the number of individuals who could locate Ukraine on a map. And that number is well above 10. So we've met the first condition. The second condition was that n times q hat must be at least 10. And 2005 times 0.6584, our value for q hat, is equal to 1320. And that number actually ends up being the number of failures, number of individuals who cannot locate Ukraine on a map. So we have met both conditions and can continue with the confidence interval. If we have not met one of these two conditions, then we really should be stopping here. Next, we can move on to the execute calculation step of the Phred technique. In this step, we must calculate the confidence interval by using this formula. Now we have all the values we need for the formula with the exception of the z-score. So we have a 95% confidence interval, so we can draw a normal distribution with 95% in the middle, which means we're going to have 2.5% in each of the tails. The z-score is the z-score that falls at the upper boundary of the right tail of the distribution. This is the same one we did before, which is going to be 95 plus 0.025 into inverse norm, which we already found is equal to 1.96. From there, we can go ahead and we can plug into the formula. P hat is 0.3416 plus or minus the z-score of 1.96 multiplied by the square root of p hat, 0.3416, times q hat, 0.6584, divided by n. I'm going to show you how I would type this into my calculator. So here is my TI-84 calculator. Move this a little bit to the side. And I'm going to type this in all at once. So I'm going to type in 0.3416. I'm going to do the minus first. Minus 1.96, 99396, and then that's multiplied by the square root, so second square root, 0.3416 times 0.6584 divided by 2005. And if you type it like that, just basically exactly how you see it, you should get the correct answer, which in this case is 0.3208 for the lower bound, and now we have to find the upper bound. So we have to do the same thing, but now adding. Instead of typing this all in again, you can just press the second key and then the enter key, and that will bring up your previous answer. Scroll all the way back to the beginning and change that minus sign to a plus sign. And then we will get the upper bound, which is 0.3624, it looks like. So here I am showing those two values on the PowerPoint, and those look like they do match the numbers here, 0.3624 to 4 decimals and 0.3208. All right, we only have one more thing to do, which is to draw conclusions, which is to use that template statement we had from before to write a sentence explaining exactly what we have found. And so that's going to look something like this. We are 95% confident that the interval between 32.08% and 36.24% contains the population percentage or proportion of registered voters who can locate Ukraine on a map. So in other words, from our sample, we found that it was about 34% of Americans could find Ukraine on a map, but we know that number is not probably perfectly reliable. We didn't take a census, we only had a sample. So we went and created this confidence interval, and now we're able to say with 95% confidence that the true value falls somewhere between basically 32 and 36%. And that completes our confidence interval. Okay, here's a problem for you to try. Voter turnout describes the proportion of eligible voters who actually turned out to vote. Suppose that you sample 200 eligible voters and find that only 138 of them turned out to vote. Find an interval we can be 99% confident the true voter turnout proportion falls between. So go ahead and pause the video and go ahead and do the 4 steps of the Phred technique. And you may want to rewind the video and kind of follow the steps as they were done for the previous example to make sure you're doing everything right. But please go ahead and pause the video and give this a shot. But that's all I had to talk about in this video, so I will see you in the next one.